this lecture, I will discuss about these topics, that is types of semiconductors, transport phenomena in semiconductors, then we'll see mobility of charge carriers and conductivity in metals. Right? In the previous lecture, we have discussed one classification of the semiconductors, that is direct and indirect semiconductors, or we can say direct band gap semiconductors or indirect band gap semiconductors. In direct band gap semiconductor, when the electron is falling from this conduction band to the valence band, so there is no need of any momentum change. That is the reason it is radiate the energy in the form of light, right? But in indirect band gap semiconductors, this conduction band minimum energy level and valence band maximum energy level is occurring at the different propagation constant k value. That is, the electron is need some momentum to fall from this conduction band to the valence band. So it will go to some defect state, then from the defect state it will fall to the valence band. So whenever it is happening like this, this will radiate the energy in the form of heat in the lattice itself, right? So then we have seen some examples of this direct band gap and indirect band gap semiconductors. So these are some examples of direct band gap semiconductors, that is gallium arsenide, gallium nitride, gallium antimonide, indium phosphorus, indium arsenic, indium antimonide, right? And with some energy gaps. So these are the indirect band gap semiconductors, that is generally we use silicon and germanium, and these are some compound elements: silicon carbide, aluminum arsenic, aluminum antimonide, gallium phosphorus, right? And these are the energy gaps. All these energy gaps at 300 degree Kelvin, right? Next we'll see the one more classification of the semiconductors, that is, so again two types of semiconductors are there: intrinsic semiconductor or pure semiconductor, and extrinsic semiconductor, or we can say impure semiconductor, or we can say doped semiconductors. Again, one more classification of these extrinsic semiconductors are n-type semiconductor and p-type semiconductor. See, what is this intrinsic or pure semiconductor is, see, when the silicon atom is made, and if we don't add any impure atoms, that will be a pure semiconductor. So we have to discuss about how the conductivity possible in these intrinsic semiconductors, then how the conductivity possible in extrinsic semiconductors, and how to make n-type semiconductor and p-type semiconductor, etc. That we have to discuss. Just here I am classifying these semiconductors. Right? Next, we have to discuss how the conductivity possible in semiconductors. So that is called transport phenomena, how the electrons are moving from one place to another place. So we'll see very brief, then later we'll discuss about the for particular semiconductors. Now first we'll see how the current flows in metal. So the current in metal is due to the flow of negative charges, or we can say electrons. See, the current in metal is due to flow of negative charges. Remember, only negative charges, or we can say electrons, right? So when we apply some electric field in this metal bar, the negative charges will move. So whenever these negative charges are moving, the current will be produced. That is in metal. But whereas in semiconductors, the current is due to both electrons, or we can say negative charges, and positive charges also. See, in semiconductors, the current is due to both electrons, or we can say positive charges. Generally we say these are the holes, that we'll see later. Positive charges. See, whenever this electron are moving or holes are moving, the current is possible in this semiconductor, right? Now what we do in semiconductors is, we dope this semiconductor with a impurity atoms to make this either electrons are dominant or holes are dominant, or we can say positive charges are dominant, right? Then if I apply some electric field, suppose electrons are dominant, that is, we can say n-type semiconductors, electrons are dominant. So when these electrons are moving, current is possible. Now when I dope with this, when I make this p-type semiconductors doping with some impurity atoms, then positive charges will move. So when these are moving, the current is possible, right? This is about how the current is flowing in metals and semiconductors. So when we are applying some electric field, or when these electrons are moving and the holes are moving, so we need two different currents, the names, so that also we should know. So those names are called drift current and diffusion current. So drift is very simple. When we apply some electric field and these electrons are moving, then that is called drift. So from external field we are moving those electrons. So forcefully we are moving those electrons. So that's why the name comes as drift. Drift current is when we apply some electric field, then these charges are moving, then that is called this drift current. That is forcefully we are moving these charges from one place to another place, right? So that is remember, drift means we are applying some external field to move these charges. Diffusion current is due to some concentration gradient, this diffusion will take place. That is, if I make so many number of electrons in at one place, right, so they will try to diffuse from higher concentration to lower concentration. Suppose here 100 electrons are there and in this region only 10 electrons are there. So there is a concentration gradient is existing. That is, there is a non-uniformity of these charges. So these 100 electrons will try to diffuse from this higher concentration to the lower concentration. So when these are moving and this current are due to this transport of charges, there is a current flow. So this current is called diffusion current. So whenever there is a diffusion current exists, right? So why this diffusion takes place? In from higher concentration to the lower concentration, these charges will move to make uniform, right? So there is a non-uniform concentration gradient. So whenever this at one place high concentration is there and another place lower concentration, then diffusion takes place, right? So this is about the drift and diffusion, right? Drift means we have to apply some electric field to move these charges. Diffusion means only we have to see that there is a at one place high concentration is there and another place lower concentration is there, then diffusion takes place, right? We will see how to find mobility of charge carriers in metals. Later we will find the mobility of these semiconductors also, right? So this is the charge distribution in metal. So there are so many number of atoms. So each plus represents the nucleus and inner electrons of each atom, and each atom may contain some valence electrons, right? So these red dots are represented as valence electrons. Now in the energy band diagram of metals we have seen, that is, even though we don't apply any energy in conduction band, there are some electrons, right? So those are called the valence electrons, or we can say free electrons. Whenever there is a free electrons, so they try to move randomly from one atom to another atom, right? Yes or no? So when they are moving, so we know that the charge is when the charge carriers are moving, the current will exist, right? But it is like a random motion, right? So when we see any cross-sectional area, these electrons are moving randomly. So some electrons are moving from left to right, and some electrons are moving from right to left. So across any cross-sectional area, the net amount of current is zero, the average current is zero, because on an average electrons passing through unit area in the metal in any direction as in the opposite direction in a given time. So suppose averagely if I take, suppose 100 electrons are moving from left to right, and same maybe approximately same amount of electrons will move from right to left. So the average current will be zero, right? Now if we apply some electric field, right? Suppose now if we apply some electric field epsilon, and the units are volt per meter. Now so what we do, so when we apply some electric field, so we will accelerate these electrons in a particular direction, right? Now when they are moving in a particular direction, so in this lattice there may be possible of collisions with the ions. When these collisions are happening, these electrons may lose some speed and it will reach to a steady state, right? So why there is a speed of the steady state? Because the electric field we are applying, right? So whenever we are applying or giving some energy, so they will accelerate and they will gain some speed. So when these are moving, so they may collide with some ions, then they may lose some speed and they may reach to a steady state, right? That speed will become steady state, so they are moving continuously with that speed only. So that speed is called drift speed, right? So this speed will directly proportional to the applied electric field, right? So that is the important equation. So this speed, drift speed, so we can say this is drift speed. Why it is called drift speed? Because we are applying some electric field. Whenever we are applying some field, so everything either it is a current, either it is a speed, so we will say it is a drift speed or drift current. So this drift speed will directly proportional to the applied electric field. Now when we remove this proportionality, then this will become V is equal to mu into electric field epsilon. So this is the very important equation. This drift speed is equal to mu into epsilon. So what is this mu is called? Mobility of charge carriers. Mobility of charge carriers. So here who is moving? The electrons. So mu is the mobility of electrons, or we can say simply because it is a metal, so only charge carriers are electrons, so mobility of charge carriers, right? And we should know what is the units of this mobility. So if I take V is equal to mu epsilon, so V is the speed, so drift speed, so V is simply meter per second speed, and epsilon we know electric field volt per meter. Now if I apply this, meter per second is equal to mu into volt per meter. So what is the units for mobility? So meter per second by volt per meter. See, meter is going up, so meter square by volt second. Now if I convert this meter into centimeter, so this will can become centimeter square by volt second. So we should remember the speed is always we know that is meter per second, and electric field is volt per meter, and the mobility, the units are centimeter square by volt second or meter square by volt second. This mobility indicates how the number of electrons are, what is the momentum of these electrons, so how they are moving. See, volt meter square by volt second, so how fast they are moving, so that indicates this mobility, right? Next, so we should know some theory, that is, see, this is V, that speed is directly proportional to electric field, and if you see, this mobility is indirectly proportional to the electric field. That is, if I draw the speed versus electric field V, so initially the speed increases linearly and slowly it will become constant, right? For higher electric fields, this speed will become constant. So this is very important concept. We may I think we got question from this concept. For high electric field, so what is the drift velocity, etc., right? So this is for small electric fields. The velocity is linearly increasing. For large electric fields, the speed will be constant, drift speed. Now whereas in mobility, so if I draw the mobility versus the electric field, this is somewhat different. For lower electric fields, the mobility will be almost constant, then it will decrease some proportional of 1 by root epsilon, not directly 1 by epsilon, 1 by root epsilon for smaller fields, right? So this is for a smaller electric fields almost constant. When it is increasing, so that is like 10 cube to 10 power 4, so it is somewhat decreasing with 1 by root epsilon. Later it will decrease with the 1 by epsilon. This is for larger electric fields, right? So you should remember these two graphs, this drift speed versus the electric field and mobility versus the electric field. So for smaller electric fields it is almost constant, then later it will try to decrease, but in this manner, right? From 10 cube to 10 to the power 4, 1 by root epsilon, then from 10 power 4, generally we can say large electric field means 10 to the power 7 volt per meter, right? You should remember these graphs. So this is about the mobility. So we can remember directly this expression. So sometimes they will give speed and electric field, so what is the mobility, right? So if we have to remember this expression, right? V is equal to mu into epsilon. V is drift speed, epsilon is the applied electric field, and mu is the mobility of charge carriers. So this tells us that how fast the electrons are moving, right? Now we will see how to find the conductivity in metal, right? So this is a conductor bar with a length L, and this is a cross section area of A, and it is containing some n number of electrons, right? So whenever conduction is possible means these electrons should move across any cross sectional area per unit time. That is nothing but current. We know that I, so this expression always we are using in network theory also, in the basics when I discuss, I used that one. So I is equal to simply dq by dt, and the units are ampere. Now this is the length and this is the cross section area and number of electrons. So how many number of electrons are passing through this conductor or cross sectional area per unit time? That is nothing but the current. Now this is containing number of electrons are n. For one electron, what is the charge? Q. For n electrons, what is the charge? N into Q. Right? Now simple, what is the current? I is equal to nq by t, time. Now this is one expression. Now to find the time in terms of the length and this electric field, etc., we know the speed v is equal to, what is the speed? Distance by time. Yes or no? So speed we know, that is a drift speed. Distance is how much? L, and time is capital T. Now if I replace L or T here in this case, what I will get? nq by, so T I need, so L by V. This is current. Now this is equation 1. Now if I want to find the current density, that is the current per unit area. So if I find the current density, that is J, so it is current per unit area I by A. Now what is I here? nq into V by L into A. So LA. So what is LA here? The area into the length is called the volume, right? So this is volume. Now see here, N by LA. So the number of electrons per unit volume is called the concentration of the electrons. So N is equal to N by LA. So this is electrons per meter cube or centimeter cube. So this is number of electrons per unit volume is nothing but electron concentration. This is called electron concentration. Number of electrons per unit volume, and the units are electrons per meter cube, or we can say per electrons per centimeter cube. Now this expression will become like this. J is equal to N by LA means small n into Q into V. Equation 2. Now generally this N into Q is called charge density, the rho. So rho is, what is this? Charge density. So what is the units is? Charge density means that is coulomb per meter cube, right? So these are the units. This is charge density. So sometimes we may get this charge density when we discuss the Hall effect. So that's why I'm giving this expression. The charge density is equal to the number of electrons per meter cube into the charge cube, right? Now we know the this drift speed is directly proportional to epsilon, and we can represent like this. So V is equal to mu into epsilon. Now if I replace here, what I will get? So J is equal to nq mu into epsilon. Now if you recall from this network theory concept, I told you there the Ohm's law in field theory. So that is, there we discussed something like this. The current density directly proportional to the electric field, and we have seen J is equal to sigma into electric field. Yes or no? So same we will apply here. So what is this one? This is nothing but sigma. So I can write as J is equal to sigma into electric field, right? Now what is this? Sigma is called conductivity. Conductivity, in this case we are discussing about the metal, so conductivity of metal. So what is this equation? And sigma is equal to nq into mu. So this equation we will use so many number of times for the semiconductors, like intrinsic semiconductor, extrinsic semiconductor, etc. So you have to remember nq into mu. What is the mu? Mobility of charge carriers. Q is the charge of electrons. So what is then the electron concentration, that is electrons per centimeter cube or meter cube, right? So this is the conductivity. So you have to remember this expression, then this one V is equal to mu epsilon, and this is also you have to remember, that is J is equal to nq into V, that is speed, right? So all these expressions we have to remember. So this is about the conductivity in metal. So you may get questions directly, so find the conductivity. Now what is the units of this conductivity? So sigma we know J is equal to sigma epsilon, right? So what are the units for this J conductivity? That is amps per meter square, that is current per unit area, so meter square I'm taking. This is sigma. And what is this electric field? Simply volt per meter. So what is the sigma will become? See, amps per meter square by volt per meter. So meter, 1 meter will be cancelled, so amps per volt. So can I make like this? 1 by volt per ampere into meter. What is volt per ampere? Is nothing but current, right? R is equal to V by I. So what is this? Simply ohms. So the conductivity units are 1 by ohm meter or ohm centimeter, or sometimes we will write ohm meter inverse also. These units are also very important of this conductivity, as well as any parameter. If I take, what are the units of that particular parameter? So we should know. So we can say ohm meter per inverse, or we can say 1 by ohm meter. So this is about the conductivity of this metal. We try to do some numerical based on these expressions from the previous gate questions or in the textbooks also, right? So next lecture we'll see how the conductivity possible in this intrinsic semiconductor, then extrinsic semiconductor, etc.